Okay. So after almost a year not at SFU, we still do the land acknowledgement of the ancestral and unceded territory that all of the campuses at SFU are on, because we're still offering this workshop through SFU. I personally am in New Westminster, and so that is primarily Kakite land, but I looked on a website and found out that there were a lot of other nations that at one time or another had also been in New Westminster. If anyone is interested in getting official confirmation that you're at this workshop, you can go to this web survey. I certainly don't mind if you take a picture of this slide so that you'll have the URL. And it just asks some questions about the workshop and what you've learned. And then you'll get an official entry on your co-curricular record, which is a document that's like an official transcript, but it's for things that you did at SFU outside from your classes. And it can be useful because say when you're writing a resume, having something to refer to that lists various things that you've done. Okay, so some of you have been in Q courses, some of you have not yet. So if you haven't, just, maybe go on what assumptions you're making, what information you've heard. And if you can answer this question in chat about how you think that university Q courses are different or will be different. So Camille says, I found that I have to look for a lot more practice questions by myself. They're not always offered by the prof. Yeah, I guess that really depends on who the prof is, but just in general, it's certainly more self-directed at university, for sure. Anybody else have any ideas? I'm glad you're looking for practice questions because that really is the way to go. I will tell you a few more things about maybe the nature of practice to do in the courses. I should say something about my background. I'm not like a math professor or anything like that. I did take first year calculus in university and first year sciences and did very poorly. And then I switched into social science and I took some stats course and did much better. I think I kind of modified my approach. And since I've been in this position at the Student Learning Commons, I've talked to many math professors that have a lot more expertise than me in the area. I worked at one point with a math instructor for Vancouver Community College. She was doing a term at SFU at the time in my office, and she's the one that developed this workshop. And also I've drawn upon the expertise of somebody who was a physics instructor, and now he's a learning specialist at Camosun College. And he's in a video that hopefully I'll get some time to show, but I've talked to him many times personally about this. So I'm really drawing on the expertise of people who know more than me about succeeding in quantitative courses, but it really resonates with my own experience when I think back about it. So Nina says, I think university math incorporates more concept and understanding compared to just looking at numbers. Yeah, so you are, it seems like you've got a fairly advanced and sophisticated understanding of what you need to do, because that's kind of what I get to at the end of the workshop, and that's really what the person I was just talking about, the learning specialist who used to be a physics instructor, really focuses on. So which Q course are you taking, or courses, Nina?
Right now, I'm enrolled in managerial economics, but I've had my fair share of university math.
Yeah,
Yeah, I'm currently a second year BD student, but I've had previous experience from my other university at Capilano. And
mm,
I have noticed for sure that you need to understand behind the numbers rather than just the formulas and like plugging in numbers into equations. So
mm-hmm.
concept is definitely important.
Yeah, exactly. And I will be talking about kind of how to zero in on the concepts, if, in case people are not aware of that. But yeah, I mean, I think if you came up with that, then it makes sense that you've taken a lot of Q courses at university before. Okay, so here are some of the differences that my colleague, who was a math instructor, did identify. And I guess the one I want to zero in right now is, the so-called new problems that appear on tests, because I've talked to many students, who have failed math courses, and I've asked why, and they would usually say something like that they thought they were understanding it and they did well enough on the homework, but then they would get to the exam, and usually they say it's not fair, that there was, some big problem that was worth a lot, and it was something that they had never seen before. So at the end of the workshop, I'm going to refer you to a resource that goes into how professors can kind of disguise problems, problems that draw on what you have learned or what you're supposed to have learned in the class, but they kind of make it look like it's something new, so that you have to go to the work of, really having the conceptual understanding, as Nina said, to recognize that this is just a version of problem or problems I've done before, but in disguise. And it kind of requires some creativity. I mean, and maybe one way of disguising it is that problems are backwards. So you don't necessarily think about creativity all the time with math. You think maybe art or writing or whatever might be more creative. But a lot of the time, as you get up there in math, there's more than one way to solve a problem. There are creative solutions you can think about, and you might have to think in creative ways to realize the connection between the problem you see in the test and the problems that you've done before. Yeah, and this whole, on the side, it says memorization doesn't work. Problems require more than plug and chug. So that's exactly what Nina was talking about. And the fact that it's cumulative, that I mean, I think math in high school obviously is as well, that you learn something in math and then the next thing you learn builds on it. But that can cause a real trap in university because it's moving very fast and it's cumulative. So if you, miss a class, or, maybe you get behind on doing your problems, um, then the rest of the course can completely blow by you. Like in high school, if you miss something, say you're sick for a week and then you go back, and they're on to the next concept and you don't get it because it builds on what you missed. I mean, that happened to me in high school, and it's easy enough to catch up, and you can, go talk to the teacher, they can help you, and then you've caught up, and then you can proceed. But in university, I mean, certainly, like, I do recommend going and talking to instructors or TAs, or certainly going to the math workshops. But it moves so fast that it can be hard to catch up when you miss one of the pieces. And then that's really hard because sometimes people are in the habit of cramming, not doing a heck of a lot of work during the term, um, but, cramming before exams, and it can't be crammed for because of the cumulative nature and how fast it moves. Yeah, and so there's way less hand holding, which I think is, what Camille noticed about professors not necessarily providing practice problems. That's probably one aspect of it. Yeah, and I really have noticed that professors and TAs are mostly very, very willing to help, not just in math, but in other courses. But that the perception isn't necessarily like that because, you're in this huge class and you kind of have a sense of, well, this person obviously can't help everybody in the class, and there are hundreds of people, so why would they help me? But the truth is that if you do go for help, I mean, most of the other people are thinking the same thing, so they don't. So when somebody does show up for help, usually it works out quite a bit. Yeah, and some departments, especially math and statistics, offer these workshops or open labs that you can go to. Well, I mean, not physically go to, I guess, these days, but it used to be that you could. But they're over Zoom. And it would be like a link that was active for, maybe several hours each day. And they would have TAs there, and then you would turn up on Zoom and, just kind of pop in and ask for help. Or you could, even just be on Zoom and do your homework, solving problems, just in case you need help. I mean, that's a good way to do it, just having the Zoom on and being muted and then unmuting yourself if you need to ask for assistance. And as well as having a ready source of help, it's really good for accountability, because there'll be people around you also working. And that can be very, very useful and motivating. But what I have heard from students, when we have that conversation about why they failed a math class, is, I went to the lab and it was, way too crowded and I couldn't get my help, at all because everybody was asking the TA's questions. So then I confronted a math professor about it, and he said, yeah, that's probably because they went to the lab right before an assignment was due or right before a test. And apparently in the sessions right before their assignments and tests, it's crazy crowded and it might be hard to get your question answered. But if you just, make a practice of going to the open labs and the workshops on a regular basis when there's nothing necessarily coming up, then you will readily access help because there won't be nearly as many people there. And then when you do go when it's crowded, they will know you. So I think somebody actually said that, not to pick on anybody, but in the chat when I was saying why did you decide to come here? I think somebody said, well, math isn't really my strongest. I'm not that great at it. And that's a common thing that you hear people saying. And then conversely, sometimes you get people that are really, really overconfident going into university math courses because of their background in math, or they just, maybe they've been told all their life that they're good at math. And a lot of professors have actually said, sometimes in the first year math courses, it's the ones that took AP or IB that do the worst because they're overconfident. And even though AP and IB are supposed to be like university math, they aren't as conceptually focused as university math. Like sometimes they're different skills and people can get complacent and not work as hard. So, whether you think you're good at math or you think that you're not good at math, I'd like you to kind of let go of those thoughts. Because really attitude is everything in learning in university. and also in math. So, you know, I don't think anyone has like the gene for being good at math or not being good at math. It's kind of like you work with what you have. And somebody who has always done well in math, like, you know, me, for example, I'd always done really well in math in high school. And then I went to university and I didn't use good strategies and I slacked off and various things. And, you know, so being so-called good at math, it didn't really help me. And then you get people that, you know, maybe do not have the greatest background in math. And the first thing you have to do is make sure that you are in the right level. So like one good thing is they have these pre-calculus tests and that kind of thing in the math department to make sure that you're getting in the right level course. Because if you get in a course that's way too high level, you know, it's going to blow you away. But if you're in the right level course, doing well in it is really a matter of putting in the effort, adopting good strategies, you know, and we'll talk about good versus not so good strategies, and getting help when you need it. So, you know, that's what having a growth mindset is. Like fixed mindsets, I'm good at this, I'm not good at that. That really stands in the way of academic success. But growth mindsets, you know, where you see your success as a function of effort, smart strategies, help seeking, that kind of thing, then, you know, if you have a growth mindset, then you're much more likely to succeed at something, even if you find it challenging. Okay, so yeah, before the transcript covers this, take a look at the caption. You know, the thing is, in math, it's really about solving problems for yourself. And there are a lot of good resources you can watch. Some of the professors at SFU make videos, you know, and they all would be solving problems in the class. There's a lot of Khan Academy or YouTube videos for solving various kinds of problems. And you can hire a tutor and they can show you how to solve problems. But the thing is, like, these are great resources, but it's never enough if you're not solving the problems yourself on a really regular basis. So sometimes that's where people go wrong when they hire a tutor. They spend a lot of money and the tutor mostly shows them how to solve problems. Whereas a good tutor will have you solve the problem on your own, and they'll be there. And if you get stuck, they will give you a little hint. They won't, you know, then solve the whole thing for you, but they'll give you a little hint to move you to the next step of the problem. And you can just keep solving it until you get stuck again. And then they'll give you another hint. So if you hire a tutor and they're just like, let me show you how it's done, then it probably isn't that helpful. And if you do go to these math workshops or open labs, then that is the approach that they adopt, is just trying to get you a little bit further ahead so that you can keep struggling away with the problem yourself. Okay, so the first thing is putting in the time and the effort. So if you are in a 4-unit calculus course or something, maybe not calculus, but if your course is worth 4 units, how much time a week do you think you should spend on it outside of class hours? Can I get some guesses in the chat? 12 hours, Camille says. 10. Yeah, I mean, you both are really in the right range, you know, and that's every week. I mean, that's not just weeks when you have tests coming up. So we have, and this is not just for Q courses, but this is kind of conventional wisdom among people in my profession, that you take the number of units of your course and you multiply it by 2 to 3. So there's a range, and then you would get the range of hours that you should be spending outside of class time. So this on this example is for a 3-unit course, but for a 4-unit course, it would be 8 to 12. So both people that answered were exactly in the right range. But then it's a little bit different when everything is remote, because when you were in person, if you were in a 3-unit Q course, you would have 3 units, 3 hours of lectures, or maybe 2 hours of lectures and 1 of tutorial, and you might have extra lab classes, but usually the units would correspond to the amount of in-class lecture kind of time. So you didn't have to also consider that. But some of you might be in classes where there's no live lectures, or where there would normally be 3 hours of a live lecture and there's just 1. So to whatever you figured out from your study formula from your number of units, you also need to sometimes add hours to compensate for the fact that, you're only in like 1 hour of lecture a week when you would normally be in 3, for example. But I mean, it's a lot of time, and it's best accomplished on a regular basis. So here is the contrast between like what works and what tends not to work in university Q classes. And this was, straight from my colleague who's a math instructor. So if you look at, doing problems every day works, whereas cramming does not work. So, every day I think means every day. So say you were in arts or social science classes, I'd probably be telling you, you want to do it on a regular basis. You want to get to it, every week, and the study formula still applies. But, maybe for that kind of class, it would be okay if you, have 2 days a week where you focus on it or something. But in math, it's like literally every day. You've got to have your brain in practice solving problems, like always. You don't want to get rusty. So, if you have 1 day a week where you work for 8 hours on your job, and you're just very busy and it's very hard for you to find time for homework that day, even if you just do 1 problem that day, just to kind of keep you in practice, it can really, really help. Let me see, is there any others that I want to elaborate on here? Yeah, okay. So the second last one, and the last one, that you need to like work all ranges of problems, all types of problems when you're practicing, and allow yourself to struggle. That's really, really important, as opposed to just doing the easy problems or finding the solution in the text and working backwards. Because what you're trying to do is replicate the kinds of conditions that you're going to get on the actual test. So this is coming from the professor who's was a physics instructor, and now he's a learning specialist. And he gave an example of what he was like as an undergraduate. And he said, that say there were 25 problems or something. Maybe he can do 22 out of 25, fairly easily. So he would do that, and he'd be like, well, I'm prepared for the test. I got 22 out of 25. I'm probably going to get a decent grade. I probably won't get 100%. I'm good. And he's like, no, because it's the 3 problems that you can't do that might very well be more likely to appear on the test. The test is usually like for the more difficult problems. So if you ignore the difficult problems under conditions where, you're on your own, you have as much time as you need, you're not under pressure, then you won't be used to struggling through problems when the test hits. So not only won't you be able to solve it, but it'll really rattle you, you know, so like, oh my gosh, I had, you know, this problem that is like the type that I ignored. Um, and you just won't know strategies for dealing with it. So if you have a problem, you know, in your homework or something, and you have no idea where to start, you can just like try all sorts of things, like even kind of some random things to see if they work. But you don't really want to be in that position on the actual test, especially for the first time. So you want to get used to how to solve problems, but also get used to the uncomfortable emotions that come with struggling to solve a problem that you're having difficulty with. Because for students who are not used to those emotions, that tends to be where math anxiety comes from, like where, you know, people might blank out on a test because, you know, oh my gosh, like I'm panicking so much for this question that now I can't even think straight and I can't even solve the ones that I would normally be able to solve. So being able to struggle on your own is a really fundamental skill for math courses. And that's why you really need a growth mindset, because a student with a fixed mindset would look at the problem and say, you know, it's too hard, I can't do it. End of story. And you can't do that because hard problems are going to come up on the test. Which is not to say that every time you have a hard problem in your homework, you need to, whoops, I'm just going to go back for a second, that you need to sit there for hours on end trying to solve it, you know, and bashing your head against the wall until you get it. Because, you know, if there's a piece that you're missing, then, you know, I mean, you might grasp it, but, you know, if you've gone for like, you should set a time limit. If you've gone for, say, 45 minutes trying to solve this problem and you're just bashing your head against the wall, it's still not the time to give up, but it's time to stop bashing your head against the wall and then get some help. You know, that's when you would see, okay, is the open lab on? Can I go to the open lab and get a hint? You know, or can I go on a group chat for my class and get a hint from a classmate? You know, and again, all you want is a hint. You don't want the full solution because you want to go back and be able to struggle. So set yourself a time limit for how long you're going to struggle on something without getting help, and then get help, go back to it. So that's one reason why study groups and study partners are so good, you know, in these days, even a group chat or something virtual, you know, when it's so hard and not necessarily wise to get together. But just having, you know, somebody to turn to other than the open labs or the workshops, which might very well be full, you know, if you're or not on at that time, you know, like if it's a Sunday or something and you're struggling with a problem, if you have a study group or a group chat, then there's a ready source of help there to get you to the next level. And also it can create like a lot more motivation and accountability. That's why I was saying, you know, maybe just go with your homework on a regular basis onto Zoom for the workshops, so that there'll be people working around you. You know, at least it would be the TA there working on their own work if nobody's asking them questions. And it might, you know, give you the accountability to kind of keep going. And then also the opportunity to explain parts, I would just say a hint, but, you know, to somebody else, or explain the concepts to somebody else, can really solidify them in your own mind. And then as well, you know, like Camille was saying, if you don't really have ready sources of extra practice questions, sometimes group members can develop them for each other. So we have talked about this resource, like the workshops and the open labs, and, you know, how you want to come on a regular basis. There is another source of help that the departments offer. This is really, really useful. I would probably take a picture of this if you are in biology, chemistry, math, physics. Not every course, but some of the courses in those departments have peer tutors attached to them. It's completely free, and they have been trained in this approach about just sort of giving hints as opposed to solving the problem with the person watching. So they're a really good resource. They're free, and they provide, you know, a similar service to something that you would have to pay for. Paying attention in lecture. This is the same slide that Michaela would have seen in the note-taking workshop. But, you know, basically, you want to be paying attention in lecture. It can be hard with, you know, some of the math courses are at 8:30 in the morning, and you might be kind of sleepy, which is why it's important to get, you know, a good night's sleep, because sleep is so useful for problem solving ability. If you find you get too distracted, it's useful to actually turn your video on. I know nobody likes to do that, but it's like when you're in a live lecture and you have a front row seat. You know, the people in the front row seats at the live lectures are less likely to be fooling around on their phones or, you know, talking to each other or whatever as the people in the back, because there's greater accountability. If the lectures are recorded, then you want to make sure that you're keeping up with them. I mean, especially in math classes where it's, you know, all cumulative. So I would suggest setting a regular time each week where you're going to use the recorded lecture and get through it, or maybe probably more than once a week in the case of math. But, you know, so you know that, okay, if it's Tuesday at 10 o'clock, that's what I'm doing. Take a lot of breaks, especially, you know, if the lectures are recorded, especially, you know, with things like quantitative where it's really complicated. You know, if your brain is really starting to hurt, then it's good to pause it and do something to refresh yourself and go back. And you can rewind for parts that are missing, but really don't play it at more than normal speed. At least not too much more than normal speed, because there have been studies that even 1.5 times playback really interferes with comprehension. So for any test that you take at university, not just quantitative, distributed practice is a really well-proven study strategy, which we talked about, you know, doing a little bit every day. It's particularly important in math, and practice testing. So there was actually a research study that looked at 20 years worth of research on study strategies, and these two came out on top, and really for anything. So I think people pretty much know that in Q courses you want to do practice problems, but even in classes where you have like essay test or multiple choice, you want to practice with questions as much as possible, because that's the skill. You know, answering questions is a skill that you're going to have to do on the exam, which is not to say that, you know, you have to write out 10 different 3-page essays or something, but you could, you know, make outlines for 10 different types of essays. So we did talk about all levels of difficulty, but when it comes to Q courses in particular, you need to practice with mixed problem sets without headings, because that's what the test is going to be like. So, you know, if you think of it like a classic math book, if the person just, you know, does all the exercises under, you know, section 4.1, and section 4.1 has a heading like the chain rule or something, you know, then it gives away, okay, this is all going to be the chain rule. And even if the heading wasn't there, you know, it's like, okay, well, the last 5 questions have been the chain rule. I think this one's going to be the chain rule too. But on the test, you know, there won't be any identifying information like that. You know, you might have a problem that's the chain rule, and then the next problem is completely different. And you have to really get used to recognizing types of problems without headings or cues. And that is also the key to solving these difficult problems where they're kind of in disguise, you know, because the more that you practice recognizing what kind of problem it is, the more prepared you would be for that as well. You know, especially if there's like a few different types of problems hidden within that one problem. So, you know, so definitely one good source of that are, if you are in the math department, I don't know if, you know, business would have anything equivalent, but they always have past exams on the math website. I think they want to ensure that all students have equal access, you know, whether or not you have a buddy that has taken it before or not. So, I'm just stopping so you can take pictures of the site, of the URL. That's the problem with captioning, but it's covering up the URL. But anyhow, you know, so, but really making an effort to find problem sets where like the problems are all mixed up and there's nothing giving away what type of problem it's going to be. That could be another function of a study group or a study partner too, that they can just, you know, take problems from a textbook and kind of mix them up for you or something. And so say your exam is the next morning and it's say 9 o'clock at night. What do you think the best thing is to do? Yes, you guys are so smart. Get a good sleep. Absolutely. You know, because at that point, more studying is not going to be useful. I mean, even if you've done no studying, it's not going to be useful at that point. You know, so a good rest will really ensure that your problem solving ability is in good shape. And it's not just problem solving ability. It's the same for, you know, I mean, it's particularly so in a problem solving course, but really, you know, for any course, you're going to need to remember things. You're going to need to be able to focus and that kind of thing when you write a test, and lack of sleep sabotages that. You know, even though, you know, people think, oh, I'm a really good student, I stayed up, you know, until 3 in the morning studying, I was putting in the work, but it really is shooting yourself in the foot. So I'm glad you guys know that. Okay, so now we get into the conceptual part, which, you know, is a little bit more advanced. So this study is getting kind of old now. It's from 2003, but they interviewed a bunch of professors who taught first year courses of all types, and the ones that taught first year math courses were asked, what's the #1 characteristic of successful first year math students? And they said successful students understand the relationships that exist between mathematical concepts and that formulas do not function in a vacuum. They perceive mathematics as a way of understanding a thinking process and not a collection of detached procedures to be learned and applied separately. So, you know, it's kind of interesting if you think about, say, social science classes where you might have to look at relationships between different theories and, you know, different things that happen, or arts classes where you're thinking about relationships between different pieces of literature. You know, math isn't really taught this way, especially in high school, but a lot of it is about, you know, relationships between different concepts. So if this is unfamiliar to you, I'm going to show this video, and it was made, it was actually through McMaster University, but it was with that learning specialist from Camosun, who also used to be a physics instructor. So he completely knows what he's talking about. The URL is there in case you want to rewatch it. There's another one that's even more advanced. There's problem solving 1, which is very basic, problem solving 2, and problem solving 3, which, you know, is even more advanced. It's about, it pretty much is about how to make decisions about like which type of problem you think it is. So if you go to this YouTube video, there would also be a link to that one. So I'm just looking to share the other one. Okay. That's a video I decided not to show. Okay, is it the right one? I'm going to mute my audio.
The building blocks of problem-solving courses, like physics, calculus, statistics, chemistry, are concepts. Surprisingly, concepts actually consist of a very small amount of information that, when correctly understood and applied, can solve a large range of problems. So students who are successful in problem-solving courses focus on knowing, understanding, and using that very small amount of crucial information. Research tells us these students do this by storing that crucial conceptual information in memory in a hierarchical and connected way, somewhat like a memory pyramid. Small bits of really crucial information, like the 2 or 3 key equations of a concept, are near the top of the pyramid, and larger pieces of related important information, like the definitions of terms in those equations, are farther down the pyramid. This is a very efficient memory method because it involves a small amount of information that is highly interconnected. By contrast, weaker students tend to try to memorize too much information with almost no hierarchy or connection, somewhat like a memory dumpster. So formulas, solutions, definitions, everything is just thrown into the dumpster with very little connection or elaboration to other pieces of information. And the dumpster approach may actually work in the short term. You can solve a number of problems very quickly by just memorizing a specific formula or solution. The problem is that in the long term, you have way too many formulas and solutions to remember. Also, professors will often choose exam questions that cannot be solved by referring simply to a specific memorized formula or solution. They want to test whether you really can understand and apply the concept, not just memorize a dumpster full of formulas and solutions. So how do you get out of the dumpster and really start building good conceptual pyramids? Here are some suggestions. Many students start learning a concept by trying to solve the related problems right away. So what they do is begin to look for specific formulas that match specific problems and give them the specific solution. Unfortunately, that, of course, is the dumpster method. Instead of trying to solve problems right away, I recommend that you work on getting a good conceptual understanding of that crucial small amount of information. So I recommend using a concept summary, a short checklist of 5 key categories that will help you identify and connect that crucial conceptual information before you start solving the related problems. The first category of the concept summary is the heading or title of the concept. To make this concept summary, I suggest you simply write down each category of the concept summary like this. And then fill in each of the categories for the new concept you are learning. Here's an example of a concept summary sheet with the categories filled in for the crucial information of Newton's second law. Try to choose concepts, and therefore titles of concepts, that are not too specific, but relate to a typical class of problems. In some courses, physics for example, maybe statistics, it might involve an entire chapter like Newton's second law or standard deviation. In other courses like calculus, it might involve a few sections like the derivatives of exponents and polynomials. The second category of the concept summary is the key equation or equations. And try to keep the number of key equations associated with a concept to a minimum. I suggest 1 to maybe 5 key equations per concept. The basic derivative formulas in calculus, Newton's second law in physics, and the Z-score in statistics would all be examples of the key equations associated with a concept. You can often find these key equations in the chapter summary of the textbook, and toss out the specific formulas that are special cases easily worked out from the more general equations. For example, in Newton's second law, there is a very common special case called Atwood's machine, and many students mistakenly try to memorize the formulas for Atwood's machine that are actually just specific examples of Newton's second law. The third category of the concept summary is the definition of each term in those key equations. Included with the definition of each term are the associated units. While this category of definition seems obvious enough, students who take the dumpster approach often really have no idea of the meaning of a specific term or the associated units. The fourth category of the concept summary is the additional important information. This involves information that is crucial to your use of the key equations. Here are some of the main kinds of additional important information that you need to watch for. The meaning and effect of zero values. For example, if an object is moving at constant velocity, then its acceleration is actually zero. Sign and direction conventions. For example, the slope of a line moving upward is positive, and downward lines the slope is negative. Reference values. For example, in equations of motion problems, the acceleration of gravity is 9.8 meters per second squared downward. Or in chemistry, the pH of pure water is 7.0. When a concept cannot be applied. For example, if you have nominal data in a statistics problem, you cannot use a t-test. If the acceleration of an object is not constant, you cannot use the standard equations of motion. The fifth and final category of the concept summary is your own example or explanation. If you do understand the concept you are studying, then you will find it quite easy to come up with your own example or an explanation in your own words of what that concept can do. You will also find it easier to remember the rest of this crucial information. If you can't come up with your own explanation or example, you probably need to reflect further on the meaning of the concept, or possibly get some more help in understanding that concept. Now that you have that crucial information that constitutes a concept, you're ready to start solving problems. That's what I cover in the next video of the problem solving series.
Okay, so I mean, that was a lot, but you can rewatch it. And the next one is about decision steps. We have both of the videos on our website, and I'll show you where a little bit later. I realize we're kind of at the end of when this was supposed to end. To have a little bit more, not a lot more. If you have to leave, certainly feel free, and you can come back. I'll post this recording probably by Monday, and you could just watch the rest, or you can stay, and I'm willing to stay, you know, as long as I have to answer everybody's questions. So I'll share my PowerPoint again. Yeah, so this is just basically repeating what Zach, the person in the video, gave for what a concept summary could look like. And if you want to take a photo of this, feel free. I had promised you some information about how to solve difficult problems. It has to do with how they are made. So actually I shouldn't have, I should share that webpage that links there. And I will show you just briefly. So now we're back. That video. the Zoom screen seems to always be covering the other tab that I want. Yeah, so this is on our website. It's the handout, A Better Approach to Quantitative Courses, Part 3. And there is a table that names and describes the way that professors might construct some problems that are kind of deceptive. So if you get used to like these different ways, you know, like for example, a red herring, the problem gives some numbers that you actually just need to ignore when you're solving the problem, you know, or a problem is put in backwards, or like multi-part. There's different, you know, combinations of problems where you've only seen them separately before, and that kind of thing. So if you can become familiar with these strategies that professors use to construct hard problems, and maybe work with classmates to develop practice problems of these types, then you will be a lot more prepared when you go into an exam. And the original reference to this is a textbook that was co-written by Richard Zakowski, who is the person in the video. So yeah, it might be worth looking at the original textbook, but this pretty much summarizes it. Okay, so here is how you would get to the page that has that handout and others. You go to the Learning Commons website. I will point out that this graphic, SLC Online Services, is always the first one that comes up when you go to our page. And if you click on it, it'll say everything that's available to students through the Student Learning Commons during the pandemic. Including virtual one-on-one consultations, mostly for writing and study strategies, not math tutoring. You know where to get math tutoring now. It's assigned to math peer tutors. But anyhow, so after that, you would go to this orange tab, Learning and Studying, and there's this big long index of topics that are covered. And then you'd go to types of courses, problem solving and quantitative courses, and you get a whole list of resources, including the video that I showed and the others in that series, and also the web page that I showed and others. You can also go to this one, specific subjects, and it lists, you know, all different university disciplines and pages that are particular to those disciplines. So it would have like specific resources that would be useful if you're studying math, if you're studying accounting, if you're studying physics, chemistry, like whatever your quantitative course is, there might be something more specific on that page. So do you want to like just say or put into the text box, you know, one thing that you learned here that you're going to try? You know, I think for some of you who have taken a lot of Q courses, some of this might be repetition. But I'm hoping that, you know, everybody at least got one little tidbit that they're going to do differently out of this. So I'd like to see that. So when I was a student, I sometimes would go to workshops, and I would usually, well, I don't think I've ever implemented a suggestion from an undergraduate workshop I went to. So that's why we have this slide. We want people to commit to implementing. Good. Doing problems every single day. Yeah, like that is something that's really emphasized by the math profs that I talk to. So that's a good place to start. And then Michaela, yeah, the help seeking piece for sure. And the concept summary, rather than just trying to plug numbers into formulas. So I think you're the one that said that you don't think that you're very strong in math. So I'm glad you're moving to like, you know, I might not, you know, feel inherently strong in math, but if I seek help and if I take, you know, the SMART approach by trying to understand math conceptually, I can do considerably better. Yeah, and then Minette knew that conceptual understanding was what to go for, but maybe the missing piece was how to achieve it. So yeah, going through the concept summary, and there's more materials on our website that reiterate that pyramid. Yeah, and more, you know, it's not necessarily more practice problems, but it's like a greater range of practice problems in terms of type and difficulty. So that's really good. I'm glad that, you know, various people got something out of this. And I'm just going to reiterate that if you want co-curricular record credit for this workshop, go to this URL and answer the web survey. That's the final slide. So I'm willing to stay for individual questions if you want. But, you know, keeping in mind that I think I pretty much told you everything that I know about succeeding in quantitative classes, as opposed to what a math professor might know. Could you copy this link in the chat? Yes, I can do that. Just a second.